16, 17. Anything else right now? Hallie? 13 and 7. Okay. I'm going to circle those because I'm going to hit those in a second. So 7, 13, 16, 17. What else? Great. Okay. So let me go back to the problem set for a moment so we can chat about those. All right, so I'm looking at the solution-based ones. That way we can, solve the problems together because the true-false stuff is not really, that's on you, okay? So what mass of KCl will produce a saturated solution, 500 grams of water at 20 degrees Celsius, the molar solubility of KCl at this concentration? Is this a calculation of concentration question? It doesn't really seem like it. It kind of relates to the solubility curves. Now, they're not giving you solubility curve here, but they're telling you that the molar solubility is this right here. So I want you to write that down and then think about how you'll figure out how much KCl will dissolve in 500 grams of water. One second. I'm going to write over, I need to write on a board. It is just math. It's not, it's more of a proportion math. Oh, you guys have this problem set right in front of you, right? This is in here, so yeah. So I'm actually not gonna pull it up because I need the board space to do work on. So you guys have it right in front of you. So Austin, tell me how you set that up.
I put the relationship, which was 0.456 moles over 100 grams, and then
over 100 grams of water.
Yeah.
Okay.
And then another portion, which was just moles of KCl. Over 500 grams.
Okay, so I'm okay with proportions to an extent, but this is one where it would be very appropriate.
And then 500 grams on the bottom, and then multiply 5 times 4.6.
So basically cross multiply and divide. So everybody right now solve for x. This is the kind of the work I would expect. Has anybody already done this problem? Okay. So if not, you are doing it with me because I'm doing your homework with you, right?
Yes.
People in the back, just make sure you're with me. Okay. So what's x, guys? 2.28 moles of KCl. Since we are utilizing KCl in that problem, we do need to recognize that because it's important, because the next step is to what? Get to grams, right? So what's the, everybody have your table out for me. 39.10 plus 35.45.
Wow.
Oh, wow.
What happens when you finish?
Yeah, you guys should expect that from me.
How long have you been?
7 years. I've been a chemistry lover since I was.
Many moons.
What's the biggest mistake you've made?
Failed a test one time. It was bad. Now I teach it. I had a teacher that re-taught me that material because, like, my sister and I were the good ones, and we both failed that test. And I hated that content. And now I teach it in AP, and I'm really good at teaching that now.
What was the content?
Acid base equilibrium.
Yeah, no.
Yeah, so it's
No,
great.
what? That's
It's
so
great.
easy.
Anyway, I need the molar mass, folks. So 74 point. 70. Say one more time. Jasmine. Oh. All right, and then how many grams is that total? 9.7, and then we would probably need to go to like 3 sig figs, right? So how many is that? 170 grams KCl. All right, that's number 1. All right, let's look at 4. 4.
Let's just go in order.
All right. No, I'm not doing all these. So hold on. I'm interested in doing 4. Okay, so I'm only doing the ones that I'm interested in doing right now because I know that you guys can solve some of these others. I'm going to go for a percent one in a second, okay? So let's go through 4. How would you prepare? Okay, so when you hear the word prepare, it's talking about making a solution. What equation comes to mind? The dilution equation, which is M1V1 equals M2V2. Okay, so capital M is what? Molarity. We know that's moles per liter, but molality is moles per kilogram of solvent. Okay. So quick reminder, I want to make sure you're aware. This is capital M, right? So capital M is molarity. That's moles of solute per liters of solution. Okay. Little m molality is moles of solute per
kilogram of solvent.
All right, so that's why the big M and little m make a difference. Please make sure you're verifying that on your paper. And then, I just lost my paper. There it is. Okay. So when you hear the word prepare solution, you're probably going to be using this. All right. So it told you you're preparing 300 milliliters of a 0.75 molar solution of NaBr. What's NaBr's name? Name it. Sodium bromide. Good. From a, okay, so you notice that these two were given together, right? So let's call those what? Okay, so V1 and M1, because they were collectively given together. So then the second scenario given was from a 2.50 molar stock solution, so it's going to be M2. So what are we solving for? V2. All right, so since they gave us the two together, we call those together. Those are the diluted versions. This is the stock solution. So we're going to take a little bit of stock. I don't know how much it is, but a little bit of stock. And then we're going to prepare a solution by putting it in a what? This is a side note. What do I put the little bit of stock in? What kind of flask? Volumetric flask. Okay. So I'm going to put V1 in this volumetric flask, and then I'm going to put water in until I meet the etch line, and then I have my diluted solution. So I have a really concentrated amount. I dilute it with water. That's kind of what this whole prepping a solution is. And you guys did that on Tuesday. Wednesday. No, Tuesday. One day. So you're clear. All right. So M1 V1 equals M2 V2. I'm solving for what?
V2.
So I'm dividing by M2 on both sides. So then I'm setting up mathematically with my unit, Zane. What? Zane?
0.5 molarity.
Nope. Look, I'm putting M1 V1 over M2.
Yeah.
This may not be how.
I got you 300 ml times 0.5 molarity over that 0.5.
And what units cancel, Zane? The molarities cancel, so we're solving for milliliters, which in this case, it's fine to put V as liters or as milliliters because they're going to cancel each other out, and you're going to express it in the unit that's described. So everybody, ready when you are? What is it? 90 milliliters. Good, of stock. And then you're going to put it in. So attain.
You're gonna dilute it just so you can get 300 milliliters.
So put in a V flask. Oh, sorry. What size V flask? What size volumetric flask?
300 milliliters.
All right, 300 ml one because that's the final solution volume you wanted. Good. So put in a 300 milliliter volumetric flask. Fill with water to what? Etch line. Good. And then invert just to mix it, like with your fingers, like you just did in your lab. So that's like, now I don't always ask for like explain how, but it's nice to be able to put that into perspective. Question, Evan? No? Savannah? Good? Zoe? Let me do a solutions one and I'll get some more questions from you guys. So I'm looking down at, I just saw this. Is it 5? Thank you. I was like, just lost it. So let's go through 5, which is a solution percent volume based question. You can't do all of problem set right now because you don't learn colligative properties. So there's pieces of this we're like, I haven't learned about that yet. We're going to learn about some of those today, okay? So on 5A, they say express the following concentrations by percent volume. So percent volume just means whatever what. Volume of,
Gram salt.
no, if it's percent volume, it means like volume by volume. Volume of solute over volume solution total, right? Remember, it's got to be the total times 100. Okay, so when we're solving this one, it gives us what first?
How is volume of solvent?
Solute. That's the. So guys, remember the solute is the smaller amount. The total is going to be the summative solute and solvent. All right, so Anna, what do they give you? Okay, so methanol. And they also give you, so 500 milliliters of H2O. So guys, everybody, which is the solute? The methanol, because it's the smaller amount. And then what would you consider H2O? The solvent, right? So here's the problem. We don't have a solution until we do what? Add them. So when we add them, that will be the solution. And what's the total solution volume? Good. So now how do I set this up? Yes, so 60 milliliters divided by 560, which is the total between these two here, times 100, and what's your percent? What was it, 10.7? So that was a volume by volume. You just had to make sure you were putting the total volume on the bottom. You guys go ahead and do B. You see B there, right?
Yes.
While you're working, we have some other concepts we want to discuss. Something, Zoe, number 6 on here.
Yeah, number 6.
We haven't learned that yet. That's fine. Okay. And then I'm looking at 1 through 8. So whoever asked me 7 on the concentration practice, I think I've discussed hang out with this practice problem. And then 17 and 18. I'll go back to 17. So if you guys had a question on 17 from the practice 1 through 18, the question was 2.7 grams of copper sulfate and 75 mils of solution. It's set to express it as mass by volume, percent mass by volume. So you're literally just taking what they gave you, mass, M per volume, and this is the total solution volume. So we are good to call that total because it is. So on number 7, this would be 2.7 grams copper sulfate divided by, that was mass, divided by volume, 75 milliliters. Total solution, and we'd multiply that by 100 and we would get their percent solution by mass volume. It's a mixed unit one. We don't see those terribly often, but it can exist, especially if they give you both of them equally. So what's this percent?
1.1. No. Yeah. Oh, it's different? Oh, geez.
Sorry, this is
My
number
bad.
17 on questions 1 through 18. What are the sums? 3.6%. And then you just put M by V, and that might help you remember it was a mass by volume question. All right, let's switch modes. Do you guys feel more 10-ish now?
Yes.
Yes? I hear like most, I need that you got to complete my survey so we get quizzes. 10 means like you're feeling pretty good on the concentration practices.
What about
1 means like I do not know any of this. There's a range here. Okay, what was your question? 16. Oh, I went through and I did 17. Let me go back and do 16 because it's a more difficult, challenging concentration practice. Okay. So 16 on 1 through 18. Calculate the grams of solute needed to prepare 250 milliliters of a 0.2 10 gram solution of magnesium sulfate that was volume by volume based concentration. So just because you see a percent, that should probably clear it, like can make you think of a fraction times 100, right? Because anytime we see a percent, it's always part per whole over 100. Yes?
Yeah.
Yes, so most of you guys probably set up like a proportion and solve for x. So we know it's a 250 ml solution total, right? Yeah, this is our solution. So just like we did volume by volume, that's going to be our total, 250 ml total solution. And we don't know how much of the solute to put in here, so call that x. We're going to multiply that by 100, and we'll equivalate that to our percent here. So that's 0.10 mass by volume. Sorry, I put in by B.
It would be 10 milliliters.
Well, hold on. So this is our percent. So how do I back up to solve for x? So everybody tell me what I have to do mathematically here. Divide by 100 first. So if I divide by 100 here and divide by 100 here, this one cancels. What's 0.1 divided by 100? Calculators. 0.001. Okay. So the x over 250 remains. So now how do I solve for x? Multiply by 250. So then x is equal to, oops, yeah, 0.25 grams of magnesium sulfate. So that one took, you had to think about how to set that one up. Kind of, maybe for a little longer than the others before you could approach it. You guys adjust me?
But it was just like 15, right?
It was very similar. Mm-hmm.
I don't know why, but I got 15, but
It was mass by volume. It was a mixed unit one. So, all right. So can I switch modes for a minute? Okay. So I'll continue answering questions on 15, 16, and then your 1 through 18. But I'd like for you guys to share. We're gonna hold off on this for a minute. I'd like for you guys to share your close reading. So if you have your close reading, look it out. Okay. Stand up over here if you're the candy one. Stand up over here if you're the candy one. Stand up in the back corner if you were the salty rose. Stand up here in the front corner by Jasmine if you were ice cream. And did I pass out another one? I only had 3, right? So get to your locations when we get out of the way. So ice cream's up here, sugar, and salting the roads, right? All right, number off 1 through infinity. I did. Oh, you chose another one. Hold on, 1 through. Number off, stand in line and number off.
I'm Candy. Where do I go? Thank you.
1, 2, 3, 4, 5.
All right, put your fingers on your hands so I can see where you are. This isn't that hard. Whew, okay, so then ones find themselves, go to that lab station. 2s go to the front lab station. 3s go to the back lab station. 4s come up here to the front. 5s go to the back lab station. 6s come up here to the front. 7s here someplace. Are there 8s? 8s go on. All right, find the people. Go, find the people. Who's up 5? Austin,
Me and Evan are
8. Okay, we're going to go to 8. And then there's 7s right here. 8s come over here someplace. 8s over here. Work for that with that right now, yes. You're sharing. Yeah, right now.
This is important stuff right here. That's pretty interesting. Something you're right. But I'm gonna keep on.
Take about 1 more minute if you can, Cheryl, if you can. You guys probably want to jump in another group just to listen on, just because they have some other ones that you guys didn't hear.
9 to the 8.
The 8.
Honestly, top 10 was 9.
This conversation is good sound. Sorry, I had this on second grade.
I have the first year.
Okay, because I mean, I got the stuff down and I gave them a nice little back. Yeah, I had this on second period and I was 7th grade. Listen, look, I have a piece of tape.
That thing. I'm sorry. I remember the whole thing.
Like, every day just get someone with a
It's
little
because
bit.
I need to move the desk away from the wall some. All right, guys, we're going to take a couple minutes. Let's go.
I like the Nifty pictures. Ooh.
They were pretty cool.
No, that's how it smells.
I just like
Alright, so we have some exciting news from chemistry today. We know that we're going to be talking about, well, if you looked ahead to your reading, to your problem set, you've seen this thing called freezing point depression. Who read about freezing point depression? Okay, so the salty people, right? So we potentially, right, might be getting between 1 and 3 inches of snow at like 3 a.m., right? It says so. Or wet
Or
rain.
wet snow.
I mean rain is
Wet,
right?
water's wet.
Wet snow, which is literally rain. It was handling there. It's one
I can't hear anything you guys are saying at this point. Okay, so come back to me. Come back to me. Reeling you back in.
Oh, nice.
Okay. So we're gonna talk about We're gonna talk about the differences and like why some things seem to press the freezing point of like let's say water, aka snow, right? Which would actually halt it from freezing, which is a bummer, but that's what we do. We put salt on the roads. But we're also gonna talk about why who's ever cooked spaghetti? Okay. Why when you cook spaghetti, who puts like some salt in the water first? All right, we do that because we don't want the water to boil over. So what are we actually doing to the boiling point of the water?
Lowering it.
Raising it, because if it's hot, 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 and it doesn't boil, that means you've made the boiling point higher.
Oh, yeah.
Yeah. So that it doesn't boil over.
Still.
No, it's still black pasta still cooks at the temperature at which it boils, at water normally boils, which is 100 degrees Celsius. So if we raise the boiling point, it's cooking, but it's not a hazard to the kitchen.
Is it really cooking or is it just like
It's cooking. You're cooking pasta. Okay, so, but shh, I know this is all really exciting news, but before we talk about the calculations and like the more conceptual based practice of that, we have to understand how different types of compounds act in aqueous solution. So this is NaBr, which is what again? Sodium bromide. It's a what type of compound? Ionic, covalent, metallic. Ionic. Okay, so what do ionic compounds do when they get into solution? They dissolve is really a useless term for me. I gotta hear more. They break in ions. Dissolve just means like, hey, it's surrounded by water. Woo! It doesn't really tell about what's happening to this. This ionizes. Okay, so when it ionizes, it breaks into what and what? Sodium 1 plus ion and bromine 1 minus ion. Okay, so it's 2 ions. When you should note the differences between this one and a couple of the others. Yeah, so we know ionic compounds ionize. When they ionize, they make ions, right? That's pretty easy. Then we have this one, calcium chloride, CaCl2. What does it break into? Ca. Give me the full name. 2 plus, good, because it's in group 2. You can see that over there, and good. Chlorine number 1 and chlorine number 2. There are 2 of them here, so there's a chloride ion and another chloride ion. So how many ions does this break into? 3 ions. The more ions, the more significant depression it has on the freezing point of a solution. Okay, and then we have, this is ethanol, C2H5OH. What kind of compound is it? Ionic, yeah or nay? Why are we saying no?
Because there's no metals.
Yeah, I think where's my carbon? So there's a carbon, there's a hydrogen, which is not an alkali metal, he's just living over there in the corner, and an oxygen. So non-metal, 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 guys. What is this? This is a covalent compound, good. So what do covalent things do with when they get placed in the water? The word dissolve came back up, but what does that mean?
Break down.
No. Ionize means break down. Dissolve means to get... What I just said it. Didn't you hear me? Okay, so dissolve simply means to get surrounded by water. It doesn't do anything to this. So sugar, like sugar and sucrose and glucose and all that jazz, they're just the same. They're all covalent. So the little molecule gets here. Here's the molecule. And then water is just hanging out around it. The molecule has literally just separated from other molecules like itself. So like they're granular now, but they're just surrounded by water. They don't do anything internally. Yeah.
So sugar doesn't dissolve in water?
Sugar dissolves in water. Dissolve is a really non-informative term. Sugar does not dissociate or ionize in water. Sugar dissolves, which means it just gets surrounded by water. Sugar doesn't do anything itself. Question? Yeah. Same. What's up? Simple syrup is water with sugar. The sugar is not ionized. It's just like sugar particle or sugar molecule, sugar molecule, sugar molecule. They're all together, and we just kind of just pull them apart, but they're still sugar molecules. Whereas an ionic compound, it was NaBr, but we actually literally broke it into 2 ions, which are now very different. Surrounded by water. Okay. No, just put ethanol. Okay, so what you should be really looking at here is which type of compounds makes more things in aqueous solution. So which one break into more things? Ionic. So this one, you take one molecule, you get 2 ions. You put one formula in it in, you get 3 ions. You put one ethanol in, you get 1. That's not really changing a whole lot. So that's why that makes a big difference to say, hey, I'm covalent, I don't do anything. Hey, I'm ionic, I break into ions. Which of these scenarios would yield an electrolytic solution? Ionic, because they have ions, and when I thread some electricity through here, what does the electricity do? It can kind of go from ion to ion and can travel through. And if you put your hand in there, it will come to you and shock you. Okay? All right, so I'm going to move away from the slide. I'm going to talk about the electrolytes on the next slide. Raise your hand if you've ever heard of just like electrolytes in everyday life, not in chemistry class. Gatorade, right? Okay. So, what movie was that? Gatorade. You guys know what I'm talking about? Adam Sandler. Waterboy. Thank you. Okay. That was a long time ago, wasn't it? All right. So if we have electrolytes here, there's a little positive, negative action going on in here, right? So we know that the electricity that's coming from this battery terminal can go from here, be threaded into the solution, and it bounces all the way through the solution, and then where does it go? Up into the light bulb, and then it's connected. So is this a complete or an incomplete circuit? Complete circuit, okay? Yeah.
Is that what's happening?
Yeah, because in potatoes they have a lot of potassium and magnesium ions, and it's just like, it's really sludgy, but it's still ions because there's still water content in there.
Right.
So what types of things are strong electrolytes? What types of compounds? Ions, okay, or ionic compounds. What kind of compounds do we say act ionically because we still crisscross their charges? Acids, very good. Okay, so some strong acids and strong bases like HCl and sodium hydroxide are good examples that are considered electrolytes. So what would you then classify as a non-electrolyte? Anything covalent, very good. Like sucrose, C11H22O11. No, sorry, it's 12, but I'm with 11. Glucose, C6H12O6, things like that. So creating a circuit is very difficult for them because there are no ions in solution. So that's why there's no light on the light bulb here because they were not able to complete the circuit. Yes.
So like when water says it has added electrolytes, what's that?
So water, actually I'm going to add that example here. So water itself, pure water, that's deionized, like the DI water we use in the lab, there are no ions in there, so it would not be electrolytic, pure water. So I could stand in the bathtub with pure water, assuming like I didn't have any like kind of ions on me, and I could drop the hairdryer in there and I'd be fine. But we all have like this like little bit of salty sweat that comes off of us any day, all the time. So your body would be depositing ions in the water, and that would be dangerous. So we would not do that. But when you have water with electrolytes added, is they've added like some sodium ions or potassium ions because your body needs specifically these two and some chlorine to allow your muscles to function at your neuromuscular junction. So if you take anatomy and physiology, you'll hear all about sodium ion channels.
Okay, wait. I have a question.
Right.
Okay. So, if there was like water and nobody was standing in it, and it like, say you dropped your hair dryer in, and you reached in to pick it up, it would electrocute you.
Because you would then complete the circuit. Yeah. You complete
What if you
it.
had a
So,
glove on?
no, hold on. Right, hold on. I'm gonna see if I can show you something. I just don't know if I have it in my possession. I'm not gonna electrocute you guys.
Burn yourself on.
Hold on. All right, I'm gonna go to the next slide. All right, write this down.
I told my teacher one, and she's still responding.
Guys, write this down. I'm looking for a toy, but I can't find it. I can't find it. I can't show you. Well, I can't find it. I have a little conductivity ball. So, everybody stand up and hold hands for me real fast. Now you're ready.
Grab it loose.
You're going to be in one circle.
Someone complete the circle. Izzy, complete the circle.
Oh, am I completing the circle?
Yes, ma'am.
Alright, so
Let's do the weight, y'all.
Alright, so everybody is holding physical contact with somebody, not like their clothing. So I'm gonna touch this like little piece of metal right here, because metal is a conductor of electricity, right? The plastic on the outside of the box. And then Luke's gonna touch the other side. Yeah, touch it. Okay, so Luke and I are not touching. We're not touching, right? So Graham holds, unlock hands. Okay, Zoe's on hands. No, Grant, you gotta hold it. Grant, you gotta hold it. No, Grant's gonna hold it. Okay, so Zoe, touch. Okay. Okay, okay, so the electricity is literally, we're connecting this all the way through us.
Yo, I thought I was gonna like shock us all.
Yeah, I was so ready. Your bodies are conducting.
Yeah, so I was getting ready for like the shock.
No. All right, back with me. Back with me. So the term colligative property is just a physical property, but we call it a colligative property specifically because a solution can generally have one property. Like if I just said, hey, Jeopardy question, what's the boiling point of pure water? Boiling point of pure water, 100 degrees Celsius. So pure water is not a solution because it doesn't have a solute in it. So a pure solution has a characteristic or a property. I'm sorry, a pure solvent has a specific property or a specific characteristic. But as soon as we make that solvent a solution, we change or we modify its properties. A lot of those properties that we're going to be speaking of are freezing point and boiling point, but there are other properties as well, like vapor pressure, and number 4, I'll add it here, osmotic pressure. We won't calculate that one though. So who's heard of osmotic before? Kind of sounds like osmosis. So your osmosis flow of water from high to low concentration is actually being caused by a certain amount of pressure. So basically, the solution has a different property than the solvent. That's like the most basic I can make that. The solution has a different property than the solvent. So it's not really like, hey, like what exactly am I putting in this solution to make it a solution? It's how many particles do I get when I put the solute in solution. So we care about how the solute, and I'm going to put this horrible word up here, dissolves. So we're asking like ourselves, is it ionizing? Or is it just dissolving, as you guys like to say, which is called hydration. we're looking to see how many ions it's making, and that's going to really give us some information on how much the temperature changes freezing point wise or boiling point wise, and how much the vapor pressure changes. So this is going back to our examples of, we put salt in the road to stop the water from freezing. We put salt in our water to stop it from boiling over. We are artificially modifying the freezing point and the boiling point of things out in our everyday life. Give me a thumbs up when you get down to like 4 right here. Okay. Justin's head more.
You do that like extend pages.
I was just trying to make sure we were
Oh, I got it.
all there together, but since Austin requested it, did I go down too far?
No.
Okay. So as a quick reminder, VP stands for vapor pressure. And I think Grant was my atmospheric pressure and I was the boiling water. Remember like the patty cake game? Okay. So when the vapor pressure equals atmospheric pressure, that's when something boils. And that's at a specific temperature many times. And as a reminder, this is just a definition that you guys wrote down a while ago. Vapor pressure is when the gases and the liquids are in equilibrium with each other. So that's our evaporation. When liquid and gas are just going back and forth with each other. Liquid to gas, gas to liquid, liquid to gas, gas to liquid. Okay, so I'm not focusing on vapor pressure as much. The two that we spend most of our time on are these two, because they're actually they're the most fun. We can do labs and stuff with them. One group read about a food that we make by freezing point depression. Who's that? Ice cream. We're going to do a lab on Tuesday called a freezing point depression lab. And we're going to make a whole boy.
Confusing me all week because I was like, why can't they play with ice cream?
Who's they?
Because it was like, it's been on the website all week. It's like, bring in ice cream. It's our homework.
Oh, you've been thinking 4th graders been doing those? No. Okay, no, bring it. Yeah, so I will have milk. I'll have all the materials to make the ice cream. But if you guys would like to bring in sprinkles or things to put on top, I have like some sprinkles, but I don't have like the other good stuff. So yes, if you would like to bring that in, Tuesday is the day. Okay, that is the day. Yes, Tuesday's gonna be a great day. Okay. I'm gonna come back to that. We're going here first, okay? All right, I'm gonna come back to the top part. You guys like squirrel, right? Come back to me. Come back to me. You gotta stay focused. All right. So some examples that you should add to your different types or examples of colligative properties. For freezing point depression, some real world examples are these. So we know about salts on the roads. We know that helps us eliminate the potential of water freezing. And I'll tell you why in a second. Like to get your radiator in car, or like in the like a basketball, like a movable goal with like the big rubber piece in the bottom. You can freeze the next to so it doesn't freeze. It's water and antifreeze. You don't want the water to freeze.
Carbon stuff you spray in the windshield.
That is not antifreeze. You should not be putting antifreeze on your windshield.
I thought that was the stuff that you press the button and it like.
It's windshield washer fluid. It's got other stuff in there to eliminate frost.
Are you drinking
Yeah.
I was thinking of biofreeze.
Oh, yeah, something different. All right, so back to me. You guys, the off-topic conversations between is not helping me out here, okay? So write down the reason why this occurs, okay? So we know that basically what we're doing is we're dropping the freezing point, but the reason why is because we had a picture of us, like we saw how ice looked structurally. Do you guys remember what that looked like?
They were like pentagon thing?
It was a
Hexagon.
hexagon, right? So draw yourself like a little water hexagon, like this. It's not going to be beautiful, but you know, it'll work. Mine's, oh my god, it's so off. I got a 5. There we go. So we have water, and that's how it crystallizes. This is ice. But what we do is when we add, like say, salt. Now, salt is a very generic term. It just means anything ionic. The salt, my people who read that article, what kind of salt did they put on the roads? Magnesium chloride or calcium chloride or sodium chloride. They put a lot of options out there for people to use. So when I get some sodium ions floating around and some chloride ions floating around, what does the water like to do with those ions? Well, they're already broken apart. Let's go back to what water is what kind of molecule? Polar. So what does it do with things that are charged? It attracts them. So this water is like, hey, sexy, let's go over here. Okay, so it starts to break up the crystal. Okay, so it doesn't freeze because the chlorides are negative and the sodiums are positive, and there's all these ions that are more attractive, and they will then kind of like go and play with those ions, and it stops the formation of ice. That is how we halt ice from freezing. So what has to happen is the temperature has to drop like a whole lot, like, you know, multiple Celsiuses, and then the ice will kind of have to reform. Celsius, yeah. So it has to drop a whole lot, and that's when it will eventually freeze. Let's say like negative 10 degrees Celsius, negative 2 degrees Celsius is not at 0, because that is the normal freezing point of water. So that's how we artificially change the freezing point of water. We're gonna watch a quick video, and then we'll come back to these. Hold on. There's no well, everything's playing right now. My computer might explode. Hold on. Alright, let me just stop that one for a minute. The Grinch. Okay. Let's try this again.
Weather fiends out there waiting for the next big snowstorm, but before the flakes fall, armies of trucks are loaded full of one of the most important road safety tools out there, salt. And along with keeping our french fries on point, salt, like sodium chloride, has actually saved a lot of lives, and probably even more fenders, thanks to its incredible de-icing abilities. So here's a truck throwing salt all over some wintry road out there. And like everything else in the picture, you can bet that the salt is pretty cold. But this begs the question, how can it be that something that isn't hot is melting the ice? Turns out salt isn't actually about melting, it's all about freezing. So the freezing point of pure water rests at 32 degrees Fahrenheit or 0 degrees Celsius. When the temperature of water reaches the freezing point, its normally free-flowing molecules get trapped into organized crystal structures. This is how ice is formed. Salt disrupts this process. Upon hitting water, salt breaks up into 2 ions, one sodium and one chloride. These 2 ions then move around and take up space in between water molecules, pushing them apart and frustrating their potential links to form ice. This disruption is called freezing point depression. And so to put this simply, salt lowers the freezing point of water. But there's a limit. Salt can only act as a stable de-icer in temperatures above 16 degrees Fahrenheit or negative 9 degrees Celsius. And there's also another drawback to using salt. Consider that over 20 million tons of road salt is used annually in the U.S. All that salt has to go somewhere in the spring. Of those 2 ions split from dissolved salt, the chloride ions can have a potentially negative effect on the environment. Chloride can kill small aquatic critters, dehydrate and kill plants, alter the composition of ground soil near roads, and can limit water circulation that keeps lakes healthy. All that salt is also corrosive to metal, wreaking havoc on infrastructure, and oh yeah, your wheels too. For these reasons, sand is used as an abrasive as an alternative. Sand is often used because it's cheap, and maybe because folks want to avoid the whole chloride issue. The thing is, salts have a chemical advantage. Because you get 2 or more ions when they dissolve, you get way more melting power for the same handful of de-icing. So sand...
So what they're saying is that ionization matters, right? For the ice or the salts, for the salts you get 2 or more ions. That's the big important part. Your colligative property. More particles, bigger impact on your changes in temperature.
It might be cheap, but you have to use way more of the stuff, and that can leave quite the mess. Now, for super cold temperatures, sodium chloride and sand won't do the job. Some alternatives that melt ice even better include magnesium chloride, calcium chloride, potassium chloride, and potassium acetate. Potassium acetate...
So for these 2 up here, how many ions do they make?
Oh no.
So think, what's the formula for magnesium chloride? MgCl2. So when it dissolves, when it ionizes, it makes Mg2+ and Cl- and Cl- because there's 2 of them. So you make 1, 2, 3 ions versus just 2.
is particularly incredible at de-icing because it works at temperatures as low as negative 75 degrees Celsius, while the rest of the bunch work around the negative 20 degree mark. Although these alternative chemicals are better at de-icing at lower temperatures, most of them have that environment-damaging chloride too, not to mention the fact that they cost way more than table salt. And if you're buying 20 million tons a year of this stuff, well, that's a lot of money. So people, keep your eyes on the road and thank salt for the fine driving conditions. Or on the other hand, you can...
All right. Oops, sorry. No, he's done. He's done. Question.
What
Question.
is sodium acetate? That's a salt?
Yeah. Anything that is an ionic compound is considered a salt.
It's an edible salt.
Sodium acetate is what that precipitation, the supersaturated solution I did the other day, in that glass, and you're like, ooh, ah. Yeah, that was it. Alright, so write down your examples for boiling point. Can I answer your question, Anthony?
Yes.
Okay, question?
Is that just like regular salt?
It's okay, some of it's magnesium chloride, some of it can be calcium chloride. The pink part of it is actually, some of it's bacteria. So it's pigmented because of the natural environmental microbes in the environment there. So this is just an example for your boiling point elevation. We specifically would want to elevate the boiling point for situations where we want to maintain a steady hot temperature, and so boiling is kind of crazy sometimes. So the one that we often use is boiling point of like cooking spaghetti. But another way that this is useful is when you don't want, like this is a cactus, right? This is out in the hot sun. Do we want the water inside of the cactus to boil? That would totally destroy all the cells in the plant cells in the cactus. So there are ions dissolved or dissociated. I'll put the word dissociated because we haven't used that one yet, in the cactus, and so it heightens the boiling point of the water in the cactus so that it doesn't unfortunately die out in the desert. So it's a neat way of preserving animal life and plant life. Okay, I'm going past that. That was a short one. Go back up to vapor pressure because that was the one I did not do with you yet. So this is one that really relates to the attractions between molecules again. So if we have pure water, let's just call this salt and water. When does it boil? What temperature? 100 degrees Celsius, right? So the water liquid is coming off of the top of the solution in vapor form, and then the atmospheric pressure is pushing it back in, and like we have to assume this is a closed system, but we have this constant flow of it's evaporating, it's condensing, it's evaporating, it's condensing, it's evaporating, condensing. So what we can do to this pure water is we can add stuff like ions, ionic compounds to it. So you can see here, the picture kind of says it all. You've got some ions in the solution, and the ions make positive and negative, right? So what do they do with the water all dispersed throughout here? What do ions do with polar water molecules? They what? They attract them, right? So instead of allowing these, and I think this in blue, that probably wasn't a great example, instead of allowing these little gas, or these water molecules to evaporate, right, they're just escaping the top of the solution, right? They're attracted to themselves, but it's a hydrogen bond. It's strong, but it's not like so strong as an ion attraction. So the ions are basically saying, hey, I'm just going to hang on and attract to you here, here, and here. So then you have less water evaporating. So if you have less water evaporating, what does that do to your vapor pressure? Yeah, if you have less vapors, you have a lower vapor pressure. So the ions that we include in those solution now kind of halt the top of the water layer from evaporating, which makes the lower pressure caused by vapors, hence lower vapor pressure. So we do call this vapor pressure lowering, so that you remember that's decreasing the vapor pressure. Don't think vapor pressure elevation, there's no such thing as that for this case here. We called it freezing point what? Depression, because we're decreasing the freezing point, and we call it boiling point elevation because that's the only one we're increasing. You should know the directions of those. Okay, you good with this? Okay, almost. So I'm going to write an equation on the board. Delta T, write this down with me, okay? delta T, capital T, what's it stand for?
Change in temperature.
Change in temperature is equal to Ki little k, lowercase m. Right, so Chem, yep. And delta T is equal to Chem, right? So what does little lowercase m stand for? Molality. And I want to tell you what the other two stand for. Can I go forward here? Okay. So I've just written down one equation, and it's the same equation. This is the general form of it. Take a minute, read and write down some of this first, and then I'll continue explaining that equation. Where are we at here, guys?
The formula.
Formulas? Okay. So this is the slide that you should be referencing for any of the problem set questions that regard freezing point depression, boiling point elevation, things like that. So I'm going to do an example. We won't get to all of our examples today, which is fine. We can do the rest of them Monday, but you'll have a good start today. So basically we have this theory that if you put in a certain number of particles, the freezing point can be depressed by a certain amount, the boiling point can be elevated by a certain amount. But the number of particles really does matter. So you'll notice that the general equation is just delta T is equal to KIM, but there are different little K values. KFP, which is freezing point, KBP, which is talking about a boiling point elevation question, and those little K values are referencing the solute or the solvent. Solvent, right? So make sure you're clear that this is talking about the solvent, because there's actually there's maybe right on those pages there, but there are 2 pages in your book. I don't have the pictures of the tables here, but you have to be clear if you're talking about water or benzene or methanol or whatever other solvent out there. Ethylene glycol, which is antifreeze, and the ones we do use most frequently are for water. So the KB or KFP, which is a freezing point. I didn't write that down. K is the Malal freezing point or boiling point constant. So it does refer to like specifically one salt right here. So 1.86 degrees C per molal. Remember, like in capital M we said molar, and lowercase m sounds like a cool jungle cat. Wow. But boiling point is 0.512 degrees C per molal. And we know that this now is going to be a constant. We have to be given to, it would be given to us or be in a table form. And then the I factor, we call this the Van't Hoff factor. Van't Hoff factor. So guess who came up with that, guys? Some guy named Van't Hoff, right? And it's actually a inclusion of just the number of moles of ions that are being produced from a given ionic compound. And we'll do an example with the covalent. So how many ions does magnesium chloride dissociate into? How many number of ions? So here's how you would write that. If I actually ask you to write a dissociation, which there's one on your problem sets in place, dissociation equation, you take the MgCl2 and you go back to, remember doing NIEs? We had to break the ions into the number of ions we made of them. So how many magnesium ions are here? 1. But you put Mg2 plus. How many chlorine ions are here? 2. So we add 2 chloride ions. Total, we have what? 3. So the I is equal to 3. Yeah, I'm going back up. I just need some space here. So I want you guys to determine the number of ions for each of these examples here. You might need to write the equations out like that if it's helpful. It's probably very helpful. Hold up on your hands how many aluminum oxide associates to. Some non-voters here, but I do have most of the same 5. So aluminum oxide breaks into how many aluminum ions? 2 of them with a charge of what? Good, because aluminum is in group 3, 3 plus charge. And how many oxygen ions? 3, but what's the charge of oxygen? 2 minus because it's in group 6, and you can see it from crisscrossing action here. So 2 plus 3 is 5. So yes, this would be 5. How about calcium hydroxide? Hold them up. Anna, go back to your original. You guys are looking at other people, but you should be thinking about this by yourself. So I saw a couple people say 3. Raise your hand if you instinctively thought 3. A couple of us did. Okay, so this is calcium hydroxide. It's breaking into what ion and what ion? No, calcium, charge of calcium. Help me out, guys. What group is calcium in? It's in group 2, so it has a charge of 2 plus. Okay, and then the other ion is what? Hydroxide. It's its own whole polyatomic entity. Don't break it up. Don't be a homewrecker, right? It's got to be together. So there's a hydroxide with a charge of what? -1. You've memorized hydroxide, but how many are there? 2. Okay, so there's 1 plus 2 is 3. Okay, the last one, calcium carbonate, how many ions are we making? Hold it up, it's right here at your chest so I can see it. Your neighbors don't get to see it. So I want you to think about the ions that are present here. Emma, tell me what you got. Why 2? Right, carbonate is a, what is this? That's a poly, right? So it's just listed, I don't have parentheses on it, doesn't mean it's a happy family. So we made calcium ion and CO3 charge? 2 minus, there's 1 and 1, so that means the ions are 2. So who makes the biggest impact on temperature changes? Aluminum oxide, but aluminum ions would be bad to ingest on a very regular basis. Okay, so that's called the Van't Hoff factor. You have to add up the coefficients to get the number. Okay, can I come back? Can I come back to this if I need to? Okay, so I want to calculate. I'm going to try to find a problem first. let's do this one. Okay, so we have a certain amount of sugar. It's going to decrease the freezing point of 2.5 kilograms of water. How will it change the boiling point? What will the new freezing point and boiling point be? So this is like kind of a big question, right? So let's break this down. So it's looking for how much will adding blah, blah, blah change the freezing point. So of my delta T is equal to KIM, what am I asking for? Asking for what? Somebody just said it. Say again? Well, it's like asking how much I'm going to change my freezing point. It's asking for the temperature change, right? It's asking for delta T. Okay, so it's adding 2.65 moles of sugar in 2.5 kilograms of water. Together, these can give me what? Molality, right? So we actually have this in moles already, so we're good to go. So we know M is moles of sugar per kilograms of solvent, which in this case is what? Right, water. So I need you guys to calculate for me. What? We have 2.65 moles of sugar and 2.5 kilograms of water. What's that molality? 1.06 molal, right? All right, so I have that. I know what I'm looking for. What else do I know for my equation over here? Because I know the K, because I wrote down my constants, and there was a table in your textbook with that. So the K, let's do KFP first. What's the KFP, guys? Degrees C per molal. And what's the KBP? Okay, degrees Celsius per molal. There we go. So those are just what you wrote down in your notes, just the last slide. And then what else do we know? What do we know about I? So we know it's called the Van Hoff factor, but it's got to be regarding, oh, I didn't make that very clear. This is regarding the solute. So who's the solute here? The sugar. It's the thing being dissolved, right? What's the Van Hoff factor for a covalent compound? 1. Does it ionize? No. So it stays as a single entity. So the I factor here is 1 because it's covalent. Anytime you have a molecular compound or a covalent compound, the I factor is 1. So what am I now able to solve for? Delta T. So let's go ahead and plug that in for the freezing point one first. So delta T is equal to KIM. K for freezing point is 1.86 degrees C per molal. The I factor is 1 because it's covalent, okay? And the M, which you guys just found that by dividing, 1.06 molal. What units cancel? Molal, leaving me with what? Which makes sense, right? Degrees Celsius is a unit of temperature, so we're in the clear here. So at this point, calculate that for me, guys. What is it? 1.97 degrees Celsius. Okay, so if this is delta T, this is how much the freezing point is what? Changing high or low? Is it decreasing or increasing? Because we know it's called freezing point depression, so it's decreasing the freezing point. So we go back. We look at the solvent. Who's the solvent? Who's the solvent? Water. Okay, we know water's natural freezing point is what?
0 degrees Celsius.
So its original freezing point is 0 degrees Celsius. So what have I done to it? I've dropped it by how much? 1.97. So that amount is all I'm just subtracting 1.97 degrees Celsius to get what? Negative 1.97 degrees Celsius. That's it. This is the new freezing point. So I basically took my original freezing point, I'm subtracting my delta T, and I get the new freezing point. That process right there is just the backs. It's like, after we get all the calculations done, you just have to make sure you establish the new freezing point, which might take a second. Replicate that same process for the boiling point one, because the question did ask for 2. It asked for freezing point and boiling point. So run through the same delta T setup, but what are we changing here? The molality is the same. Now that's the good. The K value.
Million.
No, I can't remember it. For you. Yeah, that sounds right. And you're acting on the boiling point.
Oh, you don't.
It's elevation, remember?
It's just.
So 5, 1, 2, right?
Yeah.
Okay. Is this
0.5427.
point what?
54272.
I'm just gonna stop there. Stop half the race.
Two would be three.
Okay. So for the freezing point one, you're using just using a different constant for K. The I is still the same, the molality is still the same, but what's the new boiling point of water?
100.
So you're adding this, you're adding the delta T to the water's original boiling point of 100 degrees Celsius, so then total is 100.543 degrees Celsius. On a scale of 1 to 10, and I'm just going to show right, tell me how you feel about this water.
Hey.
We have more than most of us have more than one. Alright. I want you guys to try number 2. And then we're done, okay? Try number 2. We're done. Notice there's some similarities between 1 and 2, so you don't waste any time doing it. Can I scroll up a little bit, guys? Yeah, I need to hear you good. Can I scroll up? Move my stuff. Oh. Okay, so I know some of us maybe have seen the light. What's the difference between the first problem and the second problem? Okay, so sodium fluoride has an I of what? 2. So what's happening to all the temperature changes? They're doubling, right? So the first one, so you probably realize this too, but if you back your decimal up to get kilograms, this is the same exact molality. It was 1.06 as from the first one. What's your delta T here? For the freezing point one? 3.97? Something around there, okay. So what's the new freezing point of water? Negative 3.97, because you're subtracting from 0, which makes it negative. What's the boiling point elevation? 1.09 degrees Celsius. So what's the new boiling point of water? 100 plus that. Okay, so 101.9 degrees Celsius. So who makes a bigger impact? Covalence or ionics? Ionics. Okay, pack up. And then we will do more of these Monday. I have a series of problems that you are going to do, but I'm going to stop. I'm not going to do those. You just have selfies to work with, and you have some problems at 15. I call it concept 15, 16, but on your title it's just concept 16. You noticed that probably. Finish up on most of that. There are a couple questions you probably still have on senior properties that you might chat with. But after, I get for example problems with this, we are done with solutions. So yeah, I mean, this is going to be fun. Tuesdays are ice cream lab, okay? Nice.
Hopefully it's snowing in 20 minutes.
No, it's not.